Hello and welcome to this tutorial. In this tutorial, we're going to be looking at a theorem and how it can be proved. In the last tutorial, we looked at quadratic inequalities and how they can be solved. But in this tutorial, we're going to be looking at the theorem and how we can go about proving this theorem. So we have a theorem that says if a1, a2, a3 all to an and b1, b2, b3 all to bn are real numbers, then this expression is less than the right hand side expression. So we have if a1 or to an and b1 or to bn are real numbers, then we have this to be true. So before we start proving this, let's try to make some assumptions and also some substitutions into the statement of the theorem. You should recall that in the first tutorial we look at different types of numbers, and one of the number types in real numbers are the natural counting numbers. That is the set of 1, 2, 3, 4. And these are numbers we use for counting 1, 2, 3, 4, 5, and 6. So therefore, if we use counting numbers as example, we can illustrate this theorem. So let's try to substitute counting numbers into this theorem and see whether this theorem stands true or not before we start proving it. So if you make a1 to be equal to 1, a2 to be equal to 2, a3 to be equal to 3, and we make b1 to be equal to 4, b2 to be equal to 5, and b3 to be equal to 6. So now substituting a1, a2, a3, b1, b2, b3 into the theorem, we're going to have a1, which is 1, multiplied by b1, which is 4, plus a2, which is 2, multiplied by b2, which is 5. And we also pick a3. So a3, which is 3, multiplied by b3, which is 6. Then we square this. So let's see whether it is less than or equal to a1 square, which is 1 square, plus 2 square, plus 3 square, 4 square, plus 5 square, plus 6 squared. Here, everything here is equal to 1024, and everything here is equal to 1074. So from here we can see that 1024 is less than 1074. So we know that this particular theorem stands true. So the question still remains, how do we prove this? So how do we prove it? Now let's start looking at the statement of the proof. Now we know that for all real number, if you pick a real number, just pick an arbitrary real number and we call this lambda. So for all real number lambda, so we can say that a1 multiplied by lambda plus b1 squared plus a2 multiplied by lambda plus b2 everything squared plus a3 multiplied by lambda plus b3 everything squared all to an multiplied by lambda plus bn everything squared is greater than or equal to 0. So if you look here very well, so we know that lambda is any real number, and you can pick a1 and b1 also as real numbers. So if you have any substitution here, this is always going to be greater than or equal to 0. Even if the expression of a1 lambda or an lambda plus bn, even if this particular expression equates to negative answer, because of the squared that we have that surround the two brackets, this is always going to be positive. If you are raising negative to the power of 2, it always turns out to be positive. And if this is a positive number, this is a positive number, positive number, positive number, it's sure we are going to have what is also a positive answer. So we know that this particular expression stands true. So with this, we are going to start and also try to prove the theorem. So if we expand and collect the like times, so we're going to expand this and collect like times. So the first thing we have is a1 lambda plus b1 squared. So we can expand this by saying a1 lambda plus b1, a1 lambda plus b1. So open this up, is a squared lambda squared, a1 squared lambda squared plus a1 b1 lambda plus again a1 b1 lambda plus b1 squared. And here collecting the like times, we have a1 squared lambda squared plus 2 a1 b1 lambda plus b1 squared. So that's the expansion of the first term. Also this term will follow the same pattern. If you have a2 lambda plus b2 squared, so expanding this is going to be a2 squared lambda squared plus 2 a2 b2 lambda plus b2 squared. So the third expression, a3 lambda plus b3 squared, and this also is going to be a3 squared lambda squared plus 2a3 b3 lambda plus b3 squared. And if you now translate this to an lambda plus bn squared, so this is going to be an squared lambda squared plus 2 an bn lambda plus bn squared. So adding all according to this, we are going to have, so what to add this, we simply add the ones with like times. So we are going to add all the expression containing lambda square together, and also all the expression containing lambda and all the constants that does not contain lambda. So here we are going to have a1 squared plus a2 squared plus a3 squared plus an squared lambda squared. So what I just did is to add all this. Again, doing the same for the expression that contain only lambda. So plus a1 b1 plus a2 b2 plus a3 b3 plus an bn lambda, and lastly all the expressions that are constant, b1 squared plus b2 squared plus b3 squared plus lastly bn squared. So after we have this, we can say let a equal to everything that we have here. So this is going to be a will be a1 squared plus a2 squared plus a3 squared plus an squared. Also we can substitute b to be equal to everything we have here, which are the b values. So this is going to be b1 squared plus b2 squared plus b3 squared plus bn squared. And also we can substitute c to be equal to all the expression that contains only lambda, which is what you have here. So which are a1 b1 plus a2 b2 plus a3 b3 plus an bn. So if you substitute a to be this, b to be this, and also c to be a1 b1 or to an bn, we can rewrite this particular expression. So we now have to remove this and turn it to A, remove all this, turn it to B, and also remove all this and turn it to C. So we are going to have A lambda squared plus 2 C lambda plus B greater than or equal to 0. So here we're going to have 2, which are all the 2's that are coming from A. So if we have this expression A lambda squared plus 2C lambda plus B greater than or equal to 0, then we can solve this using the completing the square formula of quadratic equations. So solving using if you solve using completing the square, so the first thing you have to do in completing the square is to make sure the coefficient of, we are solving for lambda in this case, to make sure that the coefficient of lambda is 1. So if you divide through by A, we are going to have lambda square plus 2C lambda over A plus B over A is greater than or equal to 0. So using completing the square, I'm going to have this to be lambda plus 2C over A lambda greater than or equal to negative B over A. So let me try to create more space here. So here is going to be lambda plus 2C over A lambda plus and a big open bracket greater than or equal to negative B over A, and again the same thing plus a big bracket squared. So if you are not used to solving quadratic equation using completing the square, this is the right time to check how it's been done. So this is how we solve quadratic equation using completing the square. So this is going to be half of the coefficient of lambda, this is lambda square, so 1 over 2 multiplied by the coefficient of lambda, which is 2C over A. So we then take the same thing into the right hand side. So this is going to be 1 over 2 multiplied by 2C over A. So 2 is going to cancel out 2 again A. So here I'm going to have lambda square plus 2C over A lambda plus C square over A square greater than or equal to negative B over A plus C square over A square. And here I'm going to join this and have lambda plus C over A squared greater than or equal to negative B over A plus C square over A square. Let me try and create more space. Okay, so yeah, if I take the right hand side to the left hand side so that I have coefficient, I have 0 at the right hand side. Okay, let me create more space. Okay, yes. So the expression I wrote is this: lambda plus C over A squared greater than or equal to minus B over A plus C squared over A squared. So taking the right hand side to the left hand side, so this is going to be lambda plus C over A squared plus B over A minus C squared over A squared greater than or equal to 0. So again, we know that this particular expression will always be negative, will always be positive. because we have it being raised to the power of 2. So even if the expression inside the bracket evaluates to negative, so with the application of squared, it will still bring it back to positive. So we know that this will always be equal to a positive answer. But for this particular expression to be equal to positive, we know that for b all over a minus c squared over a to be greater than or equal to 0, so this is simply writing b over a is greater than or equal to c squared over a squared. So now I'm taking this to the right hand side. So this is at the same time as writing b squared, b over a must be greater than or equal to c squared over a squared. And again, I can rewrite this to be equal to c squared over a squared is less than or equal to b over a. Now I've changed the symbol from greater than or equal to less than or equal to. So knowing this, then I can, if I'm multiplying both sides by a squared, then I'm going to have c squared over a squared multiplied by a squared less than or equal to b over a multiplied by a squared. So this we cancel out, and a we cancel out one of the a's here, and then we are going to have c squared less than or equal to a b. C squared less than or equal to ab. So this is the expression that we are going to be working with. So don't forget, we already substitute a, b, and c to be equal to a particular value. So then we can now bring back and resubstitute the value of a, b, and c in this expression. And we know that this is what a is, this is what b is, and this is what c is. So again, if you now substitute the value of a, b, and c back into this expression, c squared is less than or equal to ab, we should have the statement of our proof. Let me create more space by deleting this. Okay. So c squared, c is simply a1, b1 plus a2, b2 plus a3, b3 plus an, bn squared. Then we have less than or equal to a1 squared plus a2 squared plus a3 squared plus an squared multiplied by b1 squared. This is a now, so this is b2 squared plus b3 squared plus bn squared. And then we have the statement of our proof. So we have that a1 b1 plus a2 b2 plus a3 b3 all to an bn squared is always less than or equal to a1 squared plus a2 squared plus a3 squared plus an squared multiplied by b1 squared plus b2 squared plus b3 squared all to bn squared. So for every real number, a1, b1 all to an, bn. So that's how we can go about proving the theorem that we looked at the beginning of this tutorial. And the theorem simply validates what we just, the expression that we have here, that for if a1, b1 all to an, bn are all real numbers, then this particular expression